So what we should do is an operation to correct the B and convert it to a 1. Is 6 more than a B a 1? C, D, E, F, 0, 1. It would be a 1. So I can't do my addition correctly, but if we add 6 more than a B, if we've got a B in there, they're going to be C, D, E, F, 0, 1. So 6 more than a B is a 1, which should change that to a 1, ignoring my strange addition.
So 8, 9, 10. 8,
and that will
0,
actually, in this
1.
case, invoke a carry across here. Okay? And that's another thing that decimal accumulator adjust does. It checks for carries between bit 3 and 4, and also carries out of bit 7. Now, because of this adjustment, there is now, we've invoked a carry between bit 3 and bit 4. So that number will get bigger as well. So it won't just be 7 plus 2, it'll be 7 plus the 2 plus the 1, which will effectively give us a 10. 10 will eventually be an A in here. Now, the decimal accumulator adjusts, will then realise we can't have an A, and so we'll do exactly the same thing we did before and add a 6 to that. And 6 more than A should be a 0. So let's do that. So we've got an A in there. B, C, D, E, F, 0. That's 6 more. You agree with me? B, C, D, E, F, 0. And that will invoke a carry out, which is actually the correct answer. So 6 more than A becomes a 0. 6 more than a B becomes a 1. And we get a carry across there, and we get a carry out. So we would actually get the right answer, 1, 0, 1. So in summary, if I see you in the exam or doing things with your fingers, I'll know why now. At least it worked for me. The 4 things it's got to do is, first of all, it looks at the lower nibble. And in the lower nibble, it says, if it's bigger than 9, add 6. And as a consequence, that may change the carry flag, the auxiliary carry. Remember, there's 2 carries. One we normally don't care about. The auxiliary carry only deals with carries between bit 3 and bit 4. Yeah? Just remind you where bit 3 and bit 4 is. If this is a byte, we've got 0, 1, 2, 3, 4, 5, 6, and 7. So bit 3, bit 4 is between the lower nibble and the upper nibble. And there's a special carry that looks for bits being transferred across between those 2. So that's the auxiliary carry. And then we've got the proper traditional carry for greater than 7. Both of those flags, I think, at least this one is definitely in the program status word. I'm pretty sure the carry is as well, but check that. The program status word also has this special flag called OV for overflow that I'll come back to later. Remember, you are expected to know what all the bits in the program status word do. So even if I'm hopeless and can't remember it, I expect better of you that you can do that. Okay? So it's a collection of flags, and it also is the register select bits. There's 2 register select bits. What I won't necessarily expect to know is which bits are in which part of the program status word. Okay? If you know that, then so much the better. So back to BCD, decimal accumulator adjust. Step 1, if the number in the lower nibble is bigger than 9, add 6, which may or may not invoke a carry between bit 3 and bit 4.
So next time I'm going to have this thing sticking out.
Step 2, even if that wasn't the case, the number in here wasn't bigger than 9. What's left in there? If there was anyway a carry from bit 3 to bit 4, then we need to add 6 to what's in here. So an example of that would be 9 plus 7, he hopes. Adding those 2 numbers. If we do this, like kindergarten or whatever, so 9 plus 7 is 16, so that's a 6, and then a 1 carried into there. So the number that would be left is not bigger than a 9. However, remember that this is the lower nibble column, and this is above that. Effectively, in order performing this addition, there would have been a bit carry from location 3 to 4. If I write this in binary, it'll be clearer. So let's say we've got a reef.
Oh, I see what
I hope we can survive this. 0, 0, 0, 0. 9 is 1, 0, 0, 1. Okay, everyone happy with that? And then 0, 0, 0, 0, 0, 1, 1, 1. So we're adding those two numbers. So let's just add those. Even I can just about do that. So that's 1 plus 1, which is a 0, carry 1. So 0, carry 1. That's 1, 1. That's a 0, carry 1.
1.
Have I got that wrong already?
1, sorry. No, that's right.
That's right, okay. A 0 there, and then a 1.
No, the 1. 1.
I'll do it again. 1 plus 1 is 0, carry 1. So 1 plus 1 plus 0 is 0, carry 1.
Yeah, you had it right.
1 plus 1 plus 0 is a 0, carry 1. So you've got a 1 plus 0 plus a 1 is a 0, must be a carry 1. And that, which would be,
16.
that makes sense.
Yeah,
Of course it does. I don't know who said it was.
You guys suck.
If we think about that, that's binary, that's the 1s column, the 2s, the 4s, the 8s, and the 16s. We've got one lot of 16. Well, 9 plus 7 is 16, so that is the correct answer. However, you can see as a result of this addition, there was a movement from bit location 3 to bit location 4. That would have been detected by DAA, because that would have triggered the auxiliary carry would have been set as a consequence of that operation. So having done that, so there's two cases we've seen on the lower nibble. One is where, even if there isn't a carry, the first test is the number bigger than 9? If the number's bigger than 9, you've got to add 6 to it. So that's the first test, which may give rise to an auxiliary carry. The second test is, even if this number isn't bigger than 9, check the state of the auxiliary carry, and if it is already set, then you've got to add 6 to the lower nibble. So if it is bigger than 9, then add 6. If not bigger, oops, than 9, but AC equals 1, if you can just about read that, then add 6 again. So there's two tests we're doing here. I'll read it out because it's getting fainter and fainter. So, in the lower nibble, if the number is bigger than 9, add 6 to it, which may give rise to an auxiliary carry. If that test doesn't apply, try the next test. If the number in there is less than 9, or 9 or less, but there was an auxiliary carry anyway, then you've still got to add 6 to that number.
So you have to add 6 there.
So I've got an add 6 here. So you don't. If you do this one, you don't do that one as
No,
well.
no, you have to-
So here, yes, I've got to add 6, exactly. So adding 6 to this now, I'll go 0, 0, 1, 1, 0. You'll end up with 1, 0, 1, 1, 0. If you like, 1, 6, which is the correct answer in decimal. So you do those two steps on the lower nibble, and then you do exactly the same thing on the upper nibble. So DAA basically does a sequence of 4 operations that may or may not be applied. Okay? So, when you add the lower nibbles, you check to see if the number's bigger than 9 or not. If it's bigger than 9, you add 6, which may give rise to an auxiliary carry. End of this test on the lower nibble. However, if the number in there wasn't bigger than 9, you then check if the auxiliary carry was set anyway. And if it was, you still add 6. Having done that, you're doing your upper nibble addition. And then as part of the upper nibble addition result, one or two things could happen then. You could have a result in the upper nibble which is bigger than 9 again. Again, you would add 6 to the result. adding 6 to the result may well trigger a proper carry. Not an auxiliary carry, a proper carry. Obviously, when you're adding the upper nibble, you take into account the status of the auxiliary carry, because there could have been a carry in from the lower nibble. Okay? Right, I think we flogged to death BCD. It is there on those sequence of slides, but I didn't think it was totally clear from this the complete complexity of what DAA is doing. So it's actually doing 4 things, doing a sequence of tests. A couple of tests on the lower nibble, and then a couple of tests on the upper nibble. You only invoke DAA when you're doing addition. It doesn't work when you've been doing subtractions. It only gives you the correct result for additions. Now, someone a long time ago, it seems like a long time ago, last week said, why don't we just do all the straightforward addition in ordinary binary and then just convert the answer? Perfectly good suggestion. You could do that if you wanted to. But if you're doing a lot of decimal addition, I suppose this is a little bit quicker. DAA does, I think, all of those things that we're talking about in one machine cycle. So it's actually making these corrections very quickly. It's implemented in hardware to achieve this very fast. Okay. So we did that last week. And then there was an example of doing BCD addition. It's almost identical to the example for multi-byte addition that we did a couple of weeks ago. The only difference is that we're doing this, the decimal adjust. As a consequence of that, there may well be a carry out, but anyway. Then we did some subtraction, and let's go over that a bit. In fact, this is close to where we got up to, really. So very quickly, let's just do a simple one if I've got a simple one to hand. Okay, so the way that the 8051 does subtraction is effectively, it first of all converts the subtrahand, this number, to a negative representation of that number. And the negative representation is 2's complement notation. So you don't convert everything to 2's complement notation, you convert the negative numbers to 2's complement notation. So if we were performing this subtraction, 59 minus 27, we regard that as an addition. But we say it's an addition of 59 added to a negative quantity, minus 27. So the magnitude is 27, but we use 2's complement to give us the negative representation. And the way that we do that is we invert it and add 1. So we take 27, invert it, and add 1. So if 27 is this number, hopefully I've got a little bit of the pen working. It's on its last legs, but there we go. So if that apparently is 27, first of all, invert. I can just about do that. And then we add 1 to the result, plus 1. So the result is going to be adding 1 here. We've got 1, 0, 1, 0, 0, 1, 1, 1. So that is a 2's complement representation of minus 27, which I think we've got the same answer. If we now actually perform this, so that was the plus 27, and this is the inverse of it, and this is adding 1 to it, and this is our representation of minus 27, and then we're going to add it to the number 59. So, oh, grief. So something like that might just get looking. But one more emergency count. We'll give that a go. Right. 0, 0. 3 1s. 0, 1. And we've already worked out what minus 27 is. So 1, 1, 0, 0, 1, 0, 1. And we just do that as an addition now. So just adding these two numbers, 0, 0, 0, 0 is getting repetitive, 0, 1, 0 I think, 0, and I think there's going to be a carry out. Just check for me. The right answer, yeah, it looks right. And this bit, we can see it's a positive number because the most significant bit is a 0, and we're ignoring effectively the carry out here. And the value of this, the magnitude of this is 32, and 59 minus 27 is 32. So that's the end of the operation. If this bit was set, in order to know what the magnitude of the value is, you would have to do your inverse 2's complement thing. I have an example. I'm tempted to do this very quickly. Just for the hell of it. So if we did, for example, minus 9 minus 7, we want to perform that operation. Effectively, what we need to do, eventually it's going to be an addition. So, but we're going to have to turn that into its 2's complement. And we're going to turn that into its 2's complement in this case. And then just add the two things together. So let's do that. Now I've actually prepared this one earlier, so I'm just going to write it down, because we haven't got a lot of time. So that's plus 9. Then I'm going to invert it. So inverting it would give us, and then I'm going to add 1 to it. So that would give us, so that's the first step. Second thing, 7 is, so that's plus 7, invert it. Oops, can't even do that right. Okay. And then add 1 to that. And then we just perform the addition of these two numbers, this number and this number. So I'm just going to bring that one down to add to it. So that's the 1, 1, 1, 1, 0, 1, 1, 1. So adding these two numbers, we end up with, apparently, 1, 1, 1, 1, 0, 0, 0, 0. But remember adding this number to this number, so that's 1 plus 1 is a 0, carry along, do the thing, so you'll end up with this. This is got a 1 up here, so we know it's effectively, the answer's a negative number. But we want to know what the magnitude of this negative number is, and hopefully that you can work out minus 9 minus 7 is minus 16. Okay? Do you remember, when back at school you did your number lines, your zeros and all that kind of stuff? Right. So let's try and work out, is this the right answer very briefly? Well, to work out if it's the right answer, I'm going to do the reverse of the 2's complement. So first of all, I'm going to subtract 1 from that. So let's do that. So we've got 1, 2, 3, 4, 0, 0, 0, 0. I'm going to take 1 away from it. So 1 away from that should leave us, well, first of all, here's what 1 is. We can do that. Let's do that subtraction. Now, that should give us, and you can check this yourself afterwards, it should give us this number. And then having done that, you're then going to invert it, and the inverse of this should give you which that is the 16. So it should be the right answer. Okay. So generally speaking, there are some rules about subtraction of the sequence of steps that effectively the processor goes through. So generally speaking, these steps are as follows. So, and the subtraction, by the way, now that 2's complement stuff that we had to do there to perform the subtraction, you don't have to do that by hand. The 8051 will actually perform that operation as part of the subtraction. When you do sub from the accumulator immediately, I don't know, 7 decimal, this plus 7 decimal will be turned into its 2's complement equivalent and then added to the A. So that kind of operation, this manipulation that we're doing by hand, that's what this instruction will do for us. It will leave the result as it is, so you can then check the most significant bit to see if the result is a negative or a positive. So, the first thing that sub would actually do is, so step 1 would be to take 2's comp of sub, don't know how you spell this, subtrahand, I think. The second number. So that's the first thing. Step 2 is add the subtrahand, I'll just write sub t, to accumulator. If as a consequence, well, if the carry was set before this operation, by the way, you would subtract 1. We'll see that in operation. I've got an example in the slide or two. Okay? Then its third step is, having done this operation, is to invert the carry. And I've got a big complex example to show you all the steps. And then, having done that, depending on the state of the carry, if carry is equal to 1, it's negative. And if carry is equal to 0, the result is positive. Right, that wouldn't necessarily make a huge amount of sense just yet, but we're going to do a worked example. It's in the notes anyway, but we'll do it by hand too. So, and it's all, basically I'm just repeating what's on this slide here. So, let's give it a go and see what happens. So what we've got is, let me see, here's an example, and this is all the code is, and we're going to by hand do what the code is doing. Okay, so in this particular example, that's not the whole thing, is it? We're taking away, let me see, it's on the previous slide. This is the actual operation that we're performing. We're trying to do with some code. It's the very top line. So really we're saying, how do you do 2762 hex subtract 1296 hex? Now both of those numbers are bigger than 8 bits. So we have to do it in steps. Okay? So this is the hardest kind of subtraction you're going to come across. It's a multi-byte subtraction, and we're going to work our way through it by hand and check that the sequence of operations actually give you the right result. However, in terms of code to write, that's all you would need to do. So in order to perform that, first of all, we're doing the lower byte of the operation, followed by the upper byte. So, and remember the number is, I've forgotten already, I think it's 1296. Subtract, and I've forgotten the other bit.
Something.
Wrong.
Oh, wrong way round. So 2762. 2762 subtract 1296. Okay? Which apparently in hex, these are hex numbers by the way, I've got to put that in. Apparently the answer should be 14cc. But we're going to try and prove that. So, just putting that to one side a minute. So the code, effectively, we treat the operation as dealing with this byte, and then we deal with this byte. Okay, so we start with the least significant byte. And there's no carry in, we're not subtracting anything less than the units, so we're clearing the carry flag in the very first step. Okay. The carry is used as a kind of borrow, okay, but we're not borrowing anything less than a unit, so we need to clear that flag. Then we simply are moving into the accumulator the 62, this number, and then we're going to subtract the 96 from it. So we've put into the accumulator immediately 62, and then we subtracted the 96. That's the end of the operation. Remember, we're not doing anything with BCD here, so there's no decimal adjust and all that kind of stuff. This is something completely different. This is just doing straightforward subtraction, but multi-byte subtraction. Having done that, the result, we're storing it somewhere safe, because we're going to need the accumulator again to do the second subtraction. As a result of this operation, by the way, this sub could well have set the carry flag. It would set the carry flag as if it needed to borrow a number in. If you were, for example, to do, I don't know, let's go back to school. You're doing this subtraction. 7 from 2 doesn't go. Do you remember doing that? And then you say, okay, well, I'll borrow something in. So you borrow 1 from the tens. Right? And then you basically do 7 from 12, well, that's 5. And then you have to pay back. Well, the carry flag is being used for that kind of payback, so to speak. Okay? So that, now you're not having to worry about this. This is going to be handled automatically by the code, but that's, as a result of that subtraction, the carry flag might have changed state if it needed to do a payback, so to speak. In other words, when it does the next part of the subtraction, it may well have to have put something in here. Well, that something here, the payback, would come back as the carry flag. Okay, so we've stored the result of the lower byte subtraction. The carry flag may or may not be set as a result of this subtraction, and then we repeat the same process with the upper byte. So then we reload the accumulator, this time with the 27, and we subtract from the accumulator 12. You'll notice I didn't clear the carry flag between these two things. So if the carry flag had become set as a consequence of the previous operation, that will be taken into account with the subtract. So the subtract will take not just this from this, it may well take into account the carry flag. The carry flag set, it will take another 1 off the result. If you like, paying back. And then the result will be stored in R6. So that's the code to do it. We're going to look at the what's going on in detail. So, I've written some notes here. To prove to you, and to me, that it does actually work. So, I'm going to, let's rub it out, because I need this bit of board. So the general steps are, so we've got 2762 hex, and we're subtracting 1296 hex from that. So think of that as a 2-stage operation. So that's step 2, and I'm going to deal with this as step 1.